Hello, this is my lab 4 over bar magnets for Physics 2. The purpose of this lab was to find how the distance away from a bar magnet impacts the magnetic field at an observation point that is both on and off axis of the bar magnet. And also we created a code to predict the magnetic field. The findings of this lab was as the magnetic field increases, the distance away from the bar magnet needed to achieve that magnetic field decreases. The experimental magnetic dipole for this was 1.64. To find the actual magnetic field, you must consider how the magnetic field of the Earth impacts the value. We'll look more into that later. And there's a large difference between the expected and actual values of the net electric magnetic field. The key concepts for this lab was the magnetic dipole perpendicular. We have mu naught, which is over 4 pi, and that's the constant. And then we also have mu, which is the magnetic dipole as well. We also have magnetic field due to a bar magnet, is KRN. K is the magnetic dipole in this case. And then the equation we used to find K was the natural log of the magnetic field in the x direction equals N times natural log of R, the distance vector, plus natural log of k. So that allowed us to find k, and then we also had the magnetic field of a dipole. So these were just some concepts that were essential to understanding this lab. The model for this lab, our system was the observation point, which in this case was the magnetometer, which was just my phone. And the surroundings were the bar magnet. It's important to note that the electric field goes in through the south end and exits to the north end, and that's a visualization of what's going on there. The first part of this lab for the on axis was we found the magnetometer chip and we found the distance from the magnet to the sensor that produces the magnetic field in X that we were looking for. So this value changed. We recorded the distance and the exact electric field. And we repeated that multiple times. We graphed the data to get a linear regression equation, and we used that equation to find the magnetic dipole moment. For the off-axis field, we found the perpendicular distance where the net magnetic field was equal to 100 to get the y value, and then we moved up the axis the same distance that we had just found and measured the distance along the hypotenuse and recorded the x and y component of the net magnetic field and the corrected as well. So this is the data for that. The first part towards the top, you can see R20, R70. So those are just the different fields we were looking for, and we have the distance, and then that created this graph on the right. And then for the off-axis field, we found d perp, and then we also have dy, dx, dy measured, and dy corrected. And dy measured is what we found. Dy corrected is what it actually is because you have to subtract the Earth value as well, because Earth is acting on it as well. And so, important observations here is the R value decreases as the field you're looking for increases. So those are just some important observations. Here's some code that we made to observe, to predict, and verify our results. So this first part, towards the top, you're finding the magnitude of the magnetic moment. So that was calculated using this equation right here. And then once that was found, we created a function for that magnetic field. So dipole B was the function that we will access throughout the rest of the lab. So you have R mag, R hat, and then B. And then those were done using the formula stated earlier. You have a B scale observation axis. These are just ways that we can visualize different positions for the magnetic field. And then on the r-axis, the b-axis, that's just an example of how we did it. You have to access the function you had created, and then you can find d perp, and then that allows you to find the different magnetic fields at different axes. And so this is just a general visualization. So we have our bar magnet, and so you can tell that the south end is on the left and the north end is on the right because the field is entering through the south. In conclusion, as the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. We found the magnetic dipole moment to be 1.64, and there's an 80% difference in the net magnetic field between the experimental and theoretical. So not a great experiment, not great results. Possible sources of error, we had human error in measuring distance. A piece of technology nearby could have thrown off the magnetic field direction. Movement of the phone, unexpected, could have thrown off our measurements, and then also just general inconsistencies because it was just a phone app. If we hadn't orientated our experiment to compensate for magnetic north and we had instead laid out the meter stick at some intermediate angle, the magnetic field found would be different and smaller because you're not accounting for magnetic north at that point. It would change both the x and y components, but the z component does not change. And if you were to stick two identical magnets together end to end and run the experiments again, the magnitude increases because you're creating a longer magnet with about double the magnetic dipole moment. And so the measured distances of the field would decrease. Thank you.